Okay guys, today we're looking at a projectile with an asymmetric trajectory. That just means for this object that's launched from the top of a building and lands on the ground below, the upward part of the trajectory and the downward part of the trajectory are not equal time intervals. Also, the initial and final vertical positions are not the same. So we're going to solve this a little bit differently than we did for the symmetric trajectory, but a lot of the elements are going to be the same. So we know again that this is two-dimensional motion. It's moving both horizontally and vertically. So we're going to have to break that into two separate one-dimensional motions because our kinematic equations only work in 1D. So I'll break it into horizontal and vertical because I know we have a vertical acceleration of 10 meters per second squared pointing straight down, and in the horizontal direction there's no acceleration at all. So the first thing I'm going to do, I'm going to take this initial velocity of 20 meters per second and I'm going to break it into a horizontal and a vertical part. So that's my real initial velocity. I want to find the initial velocity in the vertical and the initial velocity in the horizontal direction. I'll do that with my calculator. Just again, a reminder, make sure that you're in degrees. And I'm going to find the horizontal or the adjacent side by doing 20 cosine of 30 degrees. Close the parentheses. And my initial horizontal velocity is 17.3. I'll do something similar for my vertical, or the opposite side of this triangle. That's 20 times the sine of 30 degrees. And my initial vertical velocity is 10 meters per second. Okay? The other thing I'm going to do is, like I've done before with a symmetric projectile, I'm breaking my vertical into separate parts of the trajectory because I know that there is some additional information here at the peak or the top of the path just before the object changes directions from going in a positive vertical direction to a negative vertical direction. Here the vertical velocity must be 0. We know the horizontal velocity remains constant, but the vertical velocity is changing because of that gravitational acceleration. So I'm going to say the upward part of this trajectory, I'm going to do that in red. That is just to the peak. And then for the downward part of the trajectory, I'll do that in blue, and I'll track those kinematics. And then the purple path is the entire flight path. So I'll see what information I can find in the vertical for that purple one. For the horizontal, I want to find the range. I'm being asked to find how far away from this building does it land. So that would be the total time, which I'll be borrowing from the purple column. Okay, so I've got my initial horizontal and vertical velocities, just like all kinematics problems. I'll start by listing the 5 kinematic variables. So I know I have acceleration, displacement, v initial, v final, and time. At the beginning of this motion, the horizontal velocity is 17.3 meters per second. So that's my initial horizontal velocity. And at the start of the red path, the beginning of the upward trajectory, the vertical velocity is 10 meters per second. But also, that's the beginning, the same moment in time as the purple path, or the total flight path. So the initial vertical velocity on the purple path is also 10 meters per second. Okay? A few things that I'm going to know because this is a projectile on Earth. I'll always know that the acceleration in the horizontal direction is 0 and the vertical acceleration is -10 because I have gravity and it's pointing straight down. So for all 3 of my vertical columns here, the acceleration is just that of gravity. So -10 meters per second squared. Okay, I'm going to see if I have any more information that I can get from that. If the acceleration in the horizontal direction is 0, that means the final velocity will also be 17.3 meters per second. Okay, like we saw in the last video for a symmetric projectile, it looks like I have 3 things here in the horizontal. I could try to do the kinematic equations. The only thing you're going to confirm, because the acceleration is 0, is that v initial is equal to v final. That's with the first and third kinematic equation. If you go to the second one, displacement equals v initial t plus 1/2 at squared, and since the acceleration is 0, you end up with displacement equals initial velocity times time, but both displacement and time are unknown. So we're stuck on the horizontal. We're going to need some more information. So let's go over to the vertical and see if we can gather that information. So at the end of the red path, that is when I'm at the peak of the motion. So I would say at the end of the red path, the vertical velocity is 0. So my final velocity in the vertical direction is 0, but that's the exact same moment in time as the beginning of the blue path. So at the beginning of the blue path, the vertical velocity is also 0. So that would be the initial velocity for the downward part of the trajectory. I also know that in the symmetric trajectory, for the end of the total flight path, I just took the initial velocity and flipped it over. Well, that's going to happen here. So over here, when I return to my original height, I will have a downward velocity of 10 meters per second, but that wouldn't be the total flight path. So I actually don't know what this final vertical velocity is going to be, but I do know that from my initial position to my final position, I'm going to be going down 45 meters. So that's the height of the building. So for that last trajectory, I'll put negative 45 meters because that path is going down 45 meters. And it looks like I have 3 things in the total column. I've also got 3 things in the the vertical up column. So that's enough information to start doing my kinematic equations. Okay? You'll notice on the downward trajectory, I don't have any more information. I don't know what the velocity is at the end of this. I also don't know what the total vertical displacement is going to be, because I would need to first find how high this projectile goes. So I'm going to stick with the red and the blue for the moment. I know that to get the total range or the horizontal distance, I'm going to need to borrow the time from the total trajectory. So let's start there first. I've got acceleration, displacement, and v initial. If I wanted to find time, you'll notice there are 2 ways that I could do this. I could go straight to the second kinematic equation, where displacement is v initial t plus 1/2 at squared, and I could solve for time using the quadratic formula. I really don't prefer that method. It's an interesting result. A mathematician would use the quadratic formula and they would tell you that for this path, there are 2 moments at which the object is 45 meters below where it started. For example, you would get one here, but also if you went this way in that parabola, there's also another time in which the object would be 45 meters below where it started. But that time, it would actually be negative. And that would correlate with having gone back in time. So physically, that doesn't make any sense. So the mathematician says, we solve this quadratic, we get 2 results for time. There are 2 times at which the object is 45 meters below where it started, but that negative time is non-physical. So if I use quadratic formula, I would just throw that negative time out. I prefer a different method. I'm going to try to first find the final velocity using the third kinematic equation. V final squared equals V initial squared plus 2a delta x. Now, the one thing I want to mention about this formula, it is the most dangerous of the 3 kinematic equations. The reason is this is a scalar formula. That is, we're not going to be able to determine the direction of the velocities or the displacements when we use this equation. So that should say 2a delta x, I apologize. I can solve this for the final velocity by putting in the initial, the acceleration, and the displacement, and that will give me v final squared. But I don't want v final squared, I just want v final. So of course, I'm going to take the square root. But as we learned in math, when you take the square root in an equation, you're supposed to write plus or minus. So I can do that with my initial velocity, that is 10 meters per second squared, 10 meters per second squared, plus 2 times the acceleration times the displacement, negative 45. Okay? And when I do that, just like when I did quadratic formula, I'm going to end up with 2 results. So I put in the square root of 10 squared plus 2 times negative 10 times negative 45, and I end up with 31.6 meter per second. So final velocity is plus or minus 31.6 meter per second. But as the physicist, we need to be clever. We need to look at this result, and this is the final velocity at the end of the purple path. So this is when that object is slamming into the ground. So we now need to choose which of those results is physical, which of them actually makes sense. So I'm going to, at this point, choose the negative value for the final velocity, because I know when this object slams into the ground, it's traveling downward at 31.6 meter per second. So I've got my final velocity, and then I would prefer to go to the first kinematic equation, v final equals v initial plus at, and I'm going to rearrange that to find time. So I know time is final minus initial divided by acceleration, or negative 31.6. This is why it's really important to have that negative. If you forget that negative, you're going to get a totally different value for the time. So I have my final velocity, negative 31.6, minus the initial velocity, which was 10. So minus 10 divided by the acceleration, which is negative 10. So I have in my numerator negative 31.6 minus 10, all divided by negative 10, or 4.16 seconds. So the time is 4.16 seconds. Now again, if you did the quadratic formula with the second kinematic equation, one of the times that you would have got was 4.16, and another time would have been negative, which is non-physical. So I'm going to borrow that time of 4.16, and I'm going to bring it over to the horizontal, and that is the total flight time, 4.16 seconds. So now I can find the range, how far this object traveled, and that is just initial velocity, 17.3, times the total flight time, 4.16 seconds. So this object traveled a total distance of 17.3 times 4.16, or 71.45 meters. So I found the range. You'll maybe look at that red column and say, hey, there was enough information to go even further. They've only asked me in this particular question to find the range, but with that information in the upward trajectory column, we could also figure out how high it went above the building. And with that piece of information, how high it goes above the building, we could also figure out what distance it had to fall on the downward part of the trajectory. So this particular problem, I wasn't asked to solve for that. I've got my time from the total flight time, the trajectory of the entire path, and I was able to find the range using that time. Okay? So lots of different variations, lots of different asymmetric type problems out there. If you have some that you'd like to see, just let me know. Thanks for watching.